Okay, nice. So thank you very much. Hello, everyone. So I'm Laurent Bernard from Reactive IP. Thank you very much for your interest in this presentation. I'm going to present you how you can use IPSDK machine learning tools for digital work in your project. First of all, presentation of our company. Reactive IP is a young company, totally independent, based in France, in Grenoble, founded 8 years ago, and with a very strong experience in image processing. And our job is to offer a new generation of image processing software. Our business, Reactive IP, is dedicated to scientific image processing. So our main product is IPSDK, maybe you know. It's a very powerful library, an SDK. And there is also a nice graphical interface with this library. And we offer trainings and specific development based on statement of works or based on scientific publication. The use case I will present to you, the first one is 3D gray segmentation. In this case is a FIB acquisition, but it could be a microcity. And we use smart segmentation and smart classification to segment different phases from this dataset. And the next use case is an explanation how you can use machine learning for multi-channel and multispectral images using smart segmentation. So the first one, you can see a 3D visualization of the dataset. And customer is looking for good segmentation of dark grain inside this dataset. And the objective is such images and, of course, measurement like volume, Faraday diameter, or other from this object. So first of all, you must know, and you know, I'm sure, machine learning is a very powerful tool, but it's not magic. It's not possible. There is no magic tool in image processing. So before using machine learning, you should perform pre-processing to enhance your dataset, and it's necessary to identify all possible enhancements before using machine learning tools. For example, if you see a slice of the dataset, you can see, as in many other datasets, you have some noise present in your image, and you have to apply a filter to increase the quality of this image. So you can use many filters like Gaussian, median, but of course the best one for such image is the non-local mean. And it's nice because it's possible to use it inside IPSDK with only one parameter. It's quite easy to use it. And you can have a very nice result for such image. Interest of IPSDK, it's a very fast library. And when you have a complex algorithm like a non-local mean, it's very useful to increase the speed of your algorithm. Other point, when you have defined a good parameter for your non-local mean, it's possible to generate automatically the Python script equivalent, and you can easily integrate it inside your own Python code or use it in batch if you have a lot of data set to process. Second difficulty, you have seen the same problem during the talk of Grenoble. You can have Greyscale heterogeneity inside the image. You can see intensity is very higher on the right than on the left along the x-axis. This is the profile of intensity. And it's not possible to realize a good segmentation when you have such a problem. So you have to improve the gray organization inside your image. You can use a classical algorithm like shading correction using an interpolation of your image based of paraboloid, and you create a set image for the shape. And after, you can subtract the original image by this one, and you can obtain a better image with a good organization of gray level inside your image. Third point, and I think the more difficult to increase, is the problem of slice registration. Of course, you don't have this one with a micro-CT, but you have with a beam with a FIB acquisition. If you focus on the center of the image, you can see a big deformation inside the image, and in fact, it's not the reality of the form of the grain. It's because the slices are not well registered. So we propose an original method to improve this registration. You can use a SIFT descriptor based on automatic detected high gradient point detected inside your image. The idea is first one, you detect this point using corner algorithm, for example, and after the SIFT descriptor will compute a vector from each of these points, and the registration algorithm will compute the best transformation to link this point slice by slice. And then from this image, you will have reconstructed, registered images. This one is along the z-axis, of course. And if you have a drift, it's also possible to correct the drift inside this registration. So now you have a quite good image, and you can start the machine learning from this image. How does it work? The first step is to using machine learning, you have to compute the model from some small part of the image. And after, when the model is nice, you can apply this model on the full image. So the first step is to extract some array from the dataset. So it's very easy. You just have to select a rectangle in your image, and after you locate it inside the volume using different axes of preview and using the slider, and then you cut it and you create your array. Then you can put it inside the machine learning window. This is the machine learning window. So when you are here, this window is the aim of this window is to create the model. So at the beginning, you have to define the classes present in your image. So in this case, we have 4 classes, for example. And after, you have to select feature you want to use for the forest for the random forest algorithm. So how it works? In fact, you have a feature editor. First, you select the feature you want to use. You have the choice between Gaussian, mean, erosion, dilatation, and you can select the different size of neighborhood for this feature. In fact, feature is a new image built from the original, and this feature will be used as a new channel for the classification. Last point, it's also possible to use a subsampling image. In this case, all this theater will be computed also with this subsampling. It could be very useful when you have an object with a big size. And in this case, the multi-resolution is useful. So, next step, you have to draw some annotation for each class. It's a training, so the algorithm will use your annotation to compute the best way to classify all voxel in your image. So it's a 2D or 3D algorithm as you want. And after, automatically, the smart segmentation will use a random forest to compute the best model to organize your voxel based on this training. And you will see for each theater the percent of views of each theater. Then you can improve your model using other ROE if you want. You can choose as many ROE you want. And if you want to simplify your model, you can remove some theater using a filter based on the percentage of use of each theater. When it's okay, you can save your model and you can use it directly to your full image. And because this application is computed inside IPSDK, it's very, very fast to compute it. For example, if you launch it, you have directly your 4 classes based on this model. If your interest is only for the red part of this classification, after you just have to use a threshold based of the ID of this class, and you will obtain directly your brain. Okay, but now you have to know, and now you understand, when you have the original image, the random forest will compute one image by theater. So if you have a very, very big data set, you have to multiply by the number of theater, the memory you have to use for apply the classification. And the smart classification will compute automatically the result. And of course, all these images could be very, very big, and the memory of your computer could be not enough for this computation. So there is an optimization inside IPSDK, and the idea is very simple, in fact. Automatically, IPSDK will check the memory available in your machine, and it will define the best site to work band per band, and it will take first band and compute theater only for this band. It's a very nice way to limit the dataset volume.
Right.
And smart segmentation will compute this first band, and after, again, iteratively, the smart segmentation will compute all your data. And it's a very wonderful way to and a good solution to use random forest for very big data sets. And as I told you, optimize the sorry, and And of course, you will increase the speed to generate this. As the first speaker told, the random forest for us is the best way for such a classification and the easiest concerning the time of process and the number of parameters. So, second step of this use case, the trouble is after this first segmentation, in fact, we have to grade two different grains inside the dataset. So it's a good opportunity to use the second module of machine learning. It's a smart classification. And in its case, you will use classification to range, to order the shape using metrics already defined. So the windows is very near. You just have to define the number of a class you want. But the feature now is measure. It could be area, volume, parameter, equivalent diameter, what you want. And the machine learning will, first of all, obviously, you have to select some object from each class. And machine learning will compute exactly the same as the first as a smart segmentation, a percent for each measure used inside the model. And so after it's very easy to use the model to extract the grain you want and to realize a very nice segmentation visualization 3D, and of course to compute, measure, and histogram distribution, for example, of equivalent diameter. It's a very generic use case, usable with many other datasets, and don't hesitate to test it, to use it with inside your project. Second use case, it's very close. In fact, it's also in FIB domain, but now user used two type of detector, and you need use more channel, and as you know, more channel equal more information, and will help you to optimize the segmentation. For example, you have here two images for the same dataset, and this pore is you can see this pore in both images, but for this one you can see only inside the second channel, but not inside the first. So it's necessary to mix the two channels for a good segmentation. The objective is to obtain again a nice cartography of each element inside your image. So how it works? In fact, first of all, you have to create your multi-channel image. Very simple. You have a function to do that. You can merge first image, second image, and in fact, as many images you want inside the composite image. If you have only two channels, only the first and the second channel is displayed inside red and green. But of course, if you have more channel, you can select the channel you want to see on the display. But in this case, you have two channels, and you can see you have only two values under the cursor, and only two channels in memory, and not a third at 0. And then you can use again this multi-channel image inside the smart segmentation of IPSDK. But you can see for each theater, you have a theater, one theater by channel. And in fact, you will really use every information available inside your multi-channel image. So you have your model, you apply your model from your image, and you have your result. It could be a 2D or 3D or 4D image if you want. And if you have a set of image, you can use this algorithm by using a batch, and automatically IPSDK will apply the model on each file inside the directory and save the result inside the new directory. Last slice, you understand now IPSDK works with multi-channel, but you have no limit of number of channels. Then it's possible to use smart segmentation with multispectral images. And if you have, I don't know, 10, 100 image, it's possible to create a multi-channel and use the machine learning available in IPSDK to segment such data. Because of the very optimized algorithm for the memory management, and thanks to the very fast computation algorithm.